The next talk, we move now towards atmospheric transport of radionuclides using physics-based and machine learning models. The contribution, the author, is Akshay Govardhan from Lawrence Livermore National Lab. He's not in the room at this moment, so let's play the contribution and see whether he joins us after the contribution. So please play the contribution. Thank you.
Hi, this is Akshay Govardhan from Lawrence Livermore National Lab, United States of America, and I'm going to talk about subsurface to atmospheric transport model of radionuclides using physics-based and machine learning models. So how do we connect a subsurface transport model to atmospheric model to understand the propagation of radionuclides in atmosphere coming out from the surface? So to understand this, we are planning to connect two different models. One is a subsurface model and one is the atmospheric transport model. So I'm going to talk about the atmospheric transport model, AOLIS. AOLIS is an atmospheric simulation tool. It's a very high fidelity tool, and it's based on the work done at University of Utah, Los Alamos National Lab, and Lawrence National Lab. And it's a fast running computational fluid dynamics model. It's an efficient 3D CFD model based on finite volume and can predict transport and dispersion of contaminants in urban areas as well as complex terrain. And this is really important in this case because one of the main idea of connecting the subsurface transport model to atmospheric transport model is to detect the transport of radionuclides from an underground nuclear test, right? So for that, we need to have a model, atmospheric model, which can work in complex terrain, because most of these regions where these underground nuclear test happens are really complex terrain regions. So apart from that, this model is also coupled with the Grandjean dispersion model, which can predict dispersion of particles of different sizes and their subsequent deposition on a building as well as a ground, right? And we have integrated different data sets with this model. So this is a really nice model. It's really easy to run. It requires minimal input to run. All the user needs is input latitude and longitude of the release location, and the system automatically converts a grid using the information from the terrain as well as the building database. And we have the building database of more than 100 cities already in our database, so that we can easily query any city and build a grid for that region. As I mentioned, it's also connected to the other data set. Like on the top left, you can see the meteorological field option. It's HRR is one of the most common option which is used to run the model as input. We can also use ECMWF, WRF, or GFS, whatever is needed, we can use that. Apart from that, it also have land use database integrated. Even in a small region, in an urban area, say, there might be a big park or a lake or a pond. So you need to account for these differences. So we have integrated this kind of high resolution land characteristics data with the model. Also, when you need to determine deposition, this land use characteristics come in very handy to determine how the deposition is going to take place. And we also have population databases integrated in the model, as well as global soil maps from all around the world. We have done our due diligence. We have validated our model with existing data. So this is the case for complex terrain. You can see there is a hill in the middle of the domain, and along the cross section of the hill, along the flow line, there were a lot of measurements taken at two different lines, line A and line AA, here shown in the top left figure. And the circles, the symbol shows the data point, and the black line is the model produced AOLIS results for this scenario. And as you can see, it compares really well with the model, and also as compared to other models like WRF, we are trying to compare our results with other models too, and it's doing a great job. And we have published this result in our paper in Atmosphere Journal in 2021. So this was the model, and we wanted to validate our model for more use, like for real-time xenon sensor. Can we actually use this model for predicting how transport is going to happen from xenon, and these sensors are there, so can we produce good results, right? For that, in the LYNM project, there was a React 22 campaign where they were planning to release xenon, and there were a lot of sensors around the p-tunnel region. So the first part of the project was they wanted to design the field campaign. Since we were confident about the model, we had already validated our model for complex terrain region and other dispersion studies. We decided to help them plan or design the experiment, right? So for the React 22 model campaign, we ran a bunch of Aeolus simulations and recorded results, contaminant predictions at different regions, so that they can assess how much source they need and where to keep the sensors. So for that, we made a vast tool. It's called Atmospheric Simulation Testbed, and where we ran Aeolus multiple times. You can see for different wind direction, different wind speeds, different stability, different release location, different release duration, and all this data was produced in and kept in this Jupyter notebook format, where the experimentalist, they were able to access this data, and that helped them design their experiment. So where should they keep the instruments or the sensors, right? And once this was done, the experiment happened. This is just one of the example 3D simulation done by Aeolus, and due to the complex terrain, you can see even small change in release location can lead to really different dispersion pattern, right? So that's why you need a model which can account for these kind of complex terrain features. So once the experiment happened and we had this rich data set coming out from React 22, now it was our turn to validate our model. Like how well does it compare with the React 22 data set? So a lot of campaigns happen during React 22 campaign, but we focused on one specific campaign, React 04, where there were 4 real-time xenon sensors and 1 gas sampler in closer in position, and and there were 8 positive hits within 2 kilometers, right? So this is the scheme. So you can see this is the release location on the real top of the scenario. The green one shows detect, the red one shows non-detect, and the blue one shows detect as well as the gas sampler detect. So this was the data coming out from the React 04, and this was the Aeolus simulation which did for all the React campaigns: React 01, React 02, React 03, and React 04. And as I mentioned, we chose React 04 for our validation. We went in depth. So React 04, you can see the location. The release was apron 4, and the wind speed was 6.23 meter per second, and the wind direction was almost coming out from north. Stable conditions and a really shallow boundary layer height, right? So we input all these things, but the results were not optimal. And the reason why we looked at it and like why the results were not optimal, because the wind conditions given to us, these were with which we drove our model, were at the release location. And I can see from the map, the release location is surrounded by a lot of mountains, a lot of hills. So that release wind speed and wind direction is not representative of the whole domain. And it is actually heavily influenced by the surrounding terrain. So that's why we decided to look at different monitoring towers and identified tower MTO1, which was situated on the mesa top, away from any kind of canyons or any kind of complex terrain regions. And when we plugged in our data with that model, the results actually improved a lot. And I can show you some results here. So after we use the right wind condition, the black line is the data, and the red line is the simulation, and you can see the arrival and departure of the plume is really well predicted by the model, and the peaks are also really well predicted. These are all in linear scale, not in log scale. Usually all the validation you're used to seeing log scale, but since this is not a log scale, linear scale, it looks log, but actually it is really good. So this was done, and now the next this was all about the atmospheric model, and now I'm going to talk about how we are coupling the subsurface transport model to this atmospheric transport model, Aeolus, right? So as I mentioned, radionuclides produced from UNEs can slowly migrate to the subsurface and vent to the atmosphere, where they're transported and detected downwards. And these all regions are located in remote areas surrounded by complex terrain features and greatly affect the detectability of radionuclides once they reach the atmosphere, right? So that's why there is also a part of this project we are going to do a field experiment to validate this subsurface to atmospheric transport model, SATIX, where they're going to release some stuff underground and the contaminant is going to come out through the cracks, and it will be detected downwind in this complex terrain region, right, to understand this, because we are going to couple a model, develop a model, but we need data to validate model. So this SATIX experiment is going to happen, and where we're going to use the data from this experiment to validate our model. So what are the models we are going to use? As I mentioned, we are going to use Aeolus at the atmospheric simulation tool, which is really high resolution model, can account for all the complex terrain region, urban areas, everything. And the NUFT is the versatile subsurface transport model, which can give us probabilistic xenon fluxes generated from subsurface transport model. Here you can see some of the figures over the time, how the xenon surface subsurface model produces the data, and how these concentration increases and decreases during the period of days. So the idea, since you must have seen that the xenon is emitted from the surface over days, right? So that's a long period, and we can't use this kind of CFD high resolution model to simulate something for 30-day period. So what we did was we are going to use ensembles of Aeolus model and feed these ensemble like for different wind condition, for different wind speed, since we had the experiment from the VAST I mentioned before, and we produce an ensemble of more than 2,000 Aeolus simulations. Here are the individual maps, and then feed it to a machine learning module. Input is coming from the surface transport model, so this acts like source, and when we combine the input with the machine learning module, which has this ensemble, 2,000 ensemble of Aeolus runs, we can produce a machine learning model output of how the concentration will be in this region, and that result can be compared with the data, with field data. So this is our approach of quickly, rapidly predicting how the contaminants are going to transport over days, using really high fidelity model, machine learning, artificial intelligence, and this combining the best of best and producing a credible results. And this is where we are at. We have produced this model, and we are waiting to validate our model now with the data. So as I mentioned, Aeolus largely simulation model was successfully validated, was used and successfully validated for React 22 sensor design. Validation was done using the same data, so it is really good. Like, we could use the model to design the experiment, and at the same time we can use it to validate, use that data to validate our model. So and in this thing, what we learned was the conventional understanding was to use the meteorological condition at the source location. A lot of time we do that, but that understanding is not right, especially in complex terrain region, because that can lead to suboptimal performance of the model, because that's not the right inflow condition for the whole domain. It's greatly influenced by the local terrain, so you need to be careful. And also we develop a machine learning module which can rapidly simulate atmospheric dispersion of radionuclides arising from an underground nuclear test by coupling Aeolus with output from a subsurface transport model, NUFT. So yeah, if you have any question, you can email me at goarden1@llnl.gov, and thank you for listening.
Concludes the presentation from Akshay Govardhan. He's not online, but as we said for the previous authors, if you have any question, please check Mr. Govardhan's presentation on the platform. You will have his email address there, and please send all your questions to Akshay Govardhan, to whom we thank even if he's not here.